Hi, my name is Jonas, and in this video we will look at a simple yet powerful path planner. One of the most important questions in mobile robotics is, how can I get to my desired position? The answer can be as simple as turn until you face your target, move in a straight line until you reach it, and then turn in your target direction. A more elegant way is to rotate and move at the same time. We will now look at an algorithm that allows us to do this. For this algorithm, we need to know the coordinates x and y of the robot's current and target position and the current and target orientation phi. The current position and orientation can be calculated using robot kinematics and odometry, which we covered in another video. For our path planning algorithm, we need to calculate three values. First, we calculate the distance ρ between our current position and the target position using the x and y coordinates and the Pythagorean theorem. Second, we calculate the angle gamma between the current orientation phi and the vector from the current position to the target position using the Arcus tangent and the current orientation phi. And third, we calculate the angle delta between the target orientation phi and the vector from the current position to the target position using the previously calculated angle gamma and the current and target orientation phi. With these three values, the set points for the translational velocity vrx and the angular velocity omega r of the mobile robot can then be calculated. In the calculations, we find three different constants which are denoted as k1, k2 and k3. These constants vary for different robots and need to be set experimentally. By setting these constants, we can also adjust the behavior of our path planner. K1 affects the translational velocity, K2 the angular velocity, and K3 the swerving movement when approaching a target position. Further, there are a few things to note about the path planner. If the distance ρ is 0, the angles gamma and delta are undefined and we have reached our target position. Therefore, we can set the translational and angular velocity to 0. If gamma is 0, then our calculation of the angular velocity is undefined since we would divide by 0. This can already lead to problems if gamma becomes small due to the limited numerical resolution of microcontrollers. However, using the small angle approximation, which states that sinus of gamma is approximately equal to gamma, it is possible to cancel these two terms and obtain a valid calculation for the angular velocity. Also, gamma and delta should remain between plus minus pi. Therefore, wrap the angles if necessary. It is also worth noting that the algorithm remains stable even when the mobile robot's velocities are limited. Here we see once more all the formulas for the path planner algorithm. To use it on a robot, the distance ρ, the two angles gamma and delta, as well as the translational velocity vrx and the angular velocity omega r must be recalculated in every control cycle. Thank you for following me through this video on a path planning algorithm, and I will see you in the next one.